Colleagues, we are personally acquainted with many of you here, in the auditorium and online. And we have discussed the practical implementation of the secure by design concept on a number of occasions with you over the past 5 to 6 years. With some of you, we have tried to implement trusted hardware, software systems. I would like to begin with a rhetorical, perhaps fundamental question for you to ponder during my talk. What is it that has kept us from putting this principle into practice all this time? In my view, the answer consists of at least 3 components. First, the lack of requirements, both regulatory and legal. All forms of requirements. Second, the lack of domestic CPUs and a high-quality root of trust. And third, the lack of incentives to develop trusted execution environments. A trusted execution environment is a set of technologies with hardware, software implementation that hinges on the development of microprocessor technology and its architectures. Studies by major international consultancies, such as VDC Research, indicate that in the next 10 years, the 3 CPU architectures, x86, ARM, and RISC-V will dominate. What's more, at the present time, ARM SoCs already dominate embedded systems and applications. The development of application CPUs based on the RISC-V architecture has moved from theory to practice. Most importantly, in the context of this report, each of these architectures allows for trusted execution environments. And development continues. A prime example is the ARM v9 architecture, unveiled in the spring of 2021. Yes, right now trusted environments, especially ARM-based, are mostly used in mobile devices, smartphones, tablets, etc. This segment accounts for approximately 95% of supplies. But analysis by Abbey Research shows that by 2025, the industrial IoT segment will account for up to 25% of the Internet of Things as a whole. Let me remind you that a trusted execution environment, as defined by the Confidential Computing Consortium, is an execution environment that provides a certain set of guarantees to ensure the following properties, such as data privacy, data integrity, and code integrity. I think these terms are intuitive, so I won't dwell on them too much. That said, there is the largely cliched, though still relevant notion that building a trusted hardware, software system is always a compromise between the choice of security mechanisms, implementation methods, the final cost, and the cost of an attack. Let's look at what options we currently have when building modern systems. Of course, first in line are the mechanisms we can implement, based on the system's main CPU and execution environments. We can supplement our solution with additional chips, such as Secure Element or TPM, or use a co-processor in its execution environment. That being said, relevant are the distribution of the mechanisms and the security guarantees that they are able to provide in each of the elements presented, as well as the issues of cooperation, and assessing the impact of the adopted technical solutions on the final cost of the solution. It would be useful to consider what opportunities a trusted environment based on ARM Trust Zone can give us, including which evidence of the security guarantees can be provided. Because at this point, the audience may be under the impression that our colleagues in other countries have already resolved all the issues regarding the creation of trusted hardware, software systems. Based on publicly available studies of the security assessment of software implementations of trusted environments, we can draw the relatively gloomy conclusion that overall trust in the concept itself has fallen. This is evidenced by companies that make practical use of services that focus on end users. For example, those that implement paid content management services. There are 2 interrelated factors that led to this. First, the most popular and widely used trusted environments were compromised. Second, and very importantly, some of them, as well as services implemented on their basis, turned out to be more easily compromised than services provided by the main operating system, which was generally surprising. Let's look at the reasons that made it all possible. Technical reasons. In this case, I can name the 3 main ones. The first mistake that should not be repeated is problems with architecture. The second is development bugs and insufficient testing. Also, there is the shortage, or total absence of implemented secure software development processes. And what's interesting, the lack of hardening mechanisms, which on one hand, stems from the desire to keep the minimum size of the trusted codebase, but on the other hand, facilitates the exploitation of identified vulnerabilities. It would be of additional interest to consider the consequences of these bugs. The first thing I wish to highlight is that the most in-demand services implemented in this trusted environment were the ones compromised. Specifically, the trusted storage and cryptographic services. And, of course, a service more intelligible to the audience, focused on the end user. For example, paid content management. That being said, right now I'm talking exclusively about the software-targeted attacks. The researchers used two main vectors. The first and most critical was focused on the compromise of code that gets executed with the highest privilege level. But its practical implementation involved quite a few assumptions with respect to developing an attack in the main operating system. The second vector was associated with the search for and further exploitation of the vulnerabilities in trusted applications, and with attack development through horizontal and vertical escalation of privileges in the trusted environment itself. Let's look at the situation in Russia. As things stand, at least two companies can be said to have offered the market a dual-circuit system on a chip, where the main circuit is implemented on ARMv8 architecture cores. Plans have been announced for the development and application of ARMv9 cores. What's more, CPUs based on the MIPS architecture can be used in an isolated circuit. Plans for the use of RISC-V have also been announced. But the issues remain the same. How will the security mechanisms be distributed among these circuits? How will cooperation be aligned? In our opinion, it is up to you and us. What security mechanisms OEMs will be provided with, and what services they can provide to the market, and how secure they will be. This year, at the Rus Crypto Science and Practice Conference, my colleague and our team member, Andrei Samodelev, suggested some implementation options that assigned the tasks of implementing a hardware-software root of trust to an isolated circuit. Meanwhile, for the trusted execution environment implemented on the basis of AMD Trust Zone, the task was to provide in-demand services with high security guarantees. On the topic of services, I should note that they can be divided provisionally into two groups. The first is basic or system services. The second is industry services. On the topic of basic services, I have already mentioned two of the basic and most in-demand services. These are the trusted storage and cryptographic services. We also note the market's interest in services, such as trusted control of CPU frequency and power, and trusted control of peripherals. An interesting scenario, in our opinion, is the processing of secrets for the final stages of system startup on a chip implemented on the basis of UEFI or U-boot. Industry services, I believe, are more intelligible to the audience. At present, these are secure payments and trusted content management. An interesting scenario would be the implementation of a software TPM, made possible by virtue of the TCG specification. I think this scenario may be in demand with industries accustomed to TPM-based scenarios, such as remote device attestation, for example. Yes, colleagues, we understand perfectly well just how ambitious our development of the Kaspersky TEE software product is. At the same time, we expect that our underlying technologies, the architectural principles embedded in our operating system, microkernel, Mills and Flask architecture, as well as the processes for developing immune products, will allow us to create a trusted environment and provide the required services with high security guarantees, so that the product achieves high-level certification of no less than EAL5 certification. This being the case, we calculate that the set of interrelated, Trusted components to be supplied together with the system on a chip will in turn allow OEMs to achieve optimization in the trusted hardware, software systems they develop. To optimize and reduce the product development time and the time to market, and to provide the market with the services and necessary level of security guarantees the market expects from them. Colleagues, from our point of view, the time has come for collaboration between visionary companies that are ready and willing to develop a competitive solution for the global embedded cybersecurity market, the inferior limit of which is currently estimated at $2.5 billion annually. Thank you.
Спасибо за внимание.